Welcome to the INQA. Welcome to the INQA seminar today. Tomohiro Hattori from Keio University will be speaking on effects of fixing spins in quantum annealer. Tomohiro, please start your presentation.
Okay. Thank you for introduction, and thank you for giving me this great opportunity to present my research. I'm Tomohiro Hattori from Keio University. I present effects of fixing spins in quantum annealer. This is the overview of today's presentation. I will introduce two current studies. The two topics are related to the hardware size limitations of quantum annealers, and the both topics are already published in the journal and archive preprint server. First, I introduce the paper titled Advantages of Fixing Spins in Quantum Annealing. Fixing spins is a method to overcome hardware size limitations. In this study, we review the effects of fixing spins in quantum annealing. Second, I will introduce impact of fixing spins in a quantum annealer with energy rescaling. When it comes to considering the energy range restrictions of hardware, we need to rescale energy before inputting the programs into hardware. Fixing spins, as mentioned before, is advantageous to quantum annealing. However, fixing spins sometimes generate large value of parameters. So considering the parameter range and fixing spins are important topic. In this study, we review the relations between effects of fixing spins and rescaling. Okay, let's start first paper, Advantages of Fixing Spins in Quantum Annealing. Initially, I will introduce the purpose and the background of this study. Our main question was, what happens when we fix spins in quantum annealer? And so the purpose of this study is to investigate the effects of fixing spins in quantum annealing. Recently, there have been increasing demand for solving large-scale combinatorial optimization problems. Quantum annealer is one of the promising tools for this, but they come with hardware limitations. For example, size limitations, which is the number of spins available in hardware size is limited. Second, parameter range restrictions. That is the restrictions on the input parameter range. Third, decoherence. In this first study, to overcome size restrictions, fixing spins have been proposed as a method to reduce problem size while maintaining solution quality. Previous study suggested that this method is effective for large-scale problems. However, the detailed effects on quantum annealing performance were not well understood. And so, in this study, we investigated how fixing spins impacts on quantum annealing and how it affects the energy gap and annealing dynamics. In this slide, I will explain the method of fixing spins. Fixing spins, which is method to make reduced problems, obtains high-quality solution to large-scale combinatorial optimization problems according to previous study. Fixing spins reduce the problem size by eliminating certain variables while preserving key interactions. When the original Ising model is denoted in this equation, the reduced Ising model after fixing spins is denoted like this. The longitudinal magnetic fields is changed by adding the interaction term involved with fixed spins. The interaction not involved in fixed spins remains as the original Eigen model. This diagram illustrates what happens when we fix spins. The white and red circle shows the spins and fixed spins respectively. The black arrow shows the longitudinal magnetic field, and the black line shows the interaction, and red arrows show the effects of fixing spin. As you can see, some interactions remain after fixing spins, while the other are converted into constants or magnetic field. And so the magnetic field of reduced Ising model is larger than the original Ising model. From these graphs, the effects of fixing spins is change the property of magnetic fields and reduce the size of Ising model. To evaluate the fixing spins in quantum annealer, we introduce error probability of fixing spins. Ideally, we fix spins in the direction with the same as the spin configuration of the ground state, but it is impossible in practical. The choice of values to fix is crucial in the algorithm using fixing spins. And so the previous studies have been proposed the method to select spins and values to fix. However, the best choice of them is not revealed. In this study, we introduce the error probability. The error probability is the ratio the fixed spins opposite to the ground state. And so the error probability indicates deviation in Hamming distance of fixed spins from the ground state. By using error probability, we evaluate the fixing spins in quantum annealer. This is the example of fixing spins with no errors and errors. The reduced Ising model with different error probability represent different magnetic fields like this. So using error probability, we investigate the effects of fixing spins in quantum annealing, and these models indicate different properties. Next, I explain settings. To analyze these effects, we conducted numerical simulation and experiments in D-wave annealer. The model used in this study is random Ising model. The longitudinal magnetic fields and interactions are generated from Gaussian distribution with mean zero and the deviation of unity. This table shows the settings of the annealer. We used a minor embedding, and the number of leads is 100. The solver is used advantage systems 4.1. We measure the performance using residual energy, which indicates the solution accuracy. The residual energy of reduced problems indicate the performance of only quantum annealing after fixing spins. These are the results on the D-wave annealer. The number of original Ising model is 168. The horizontal axis is the number of spins of the reduced problems. The vertical axis is the residual energy. And so the lower is better in all graphs. Figure A represents the results with no error in fixing spins. This graph shows that increasing number of spins of reduced program enlarges ledger energy large, which indicate the larger number of spins require longer annealing time to reach the ground state. Figure B represents the results with error probability equals to 0.1. From this graph, there exists an optimal point that minimizes ledger energy, balancing fixing spin accuracy and the quantum annealing accuracy. Figure C represents the results with error probability equals 0.5. This error probability indicates randomly selected values of fixing fixed spins, so the worst case of fixing spins. When the accuracy of fixing spin is insufficient, increasing the number of reduced problem is the best way to reduce ledger energy. From these results, there are appropriate number of fixing spins, which depends on the error probability of fixing spins. Also, the real situation is similar to the case of error probability equals to 0.1. So when we use the quantum annealer with fixing spins, we don't have to use all spins which we can input into a quantum annealer, because reducing some spins enhance the performance of quantum annealing. Figure D shows the results of the performance on reduced problem in quantum annealer. This graph shows the annealing time at which the ledger energy of the reduced problem becomes to non-zero differs each n. So the optimal number of reduced problem depends on annealing time. In the next slide, I introduce the results of the simulation. From quantum annealing perspective, it is important to examine the energy gap. And so we calculate the energy gap in this study. The energy gap is derived by exact diagonalization. So the number of spins is 12. This graph, the horizontal axis is the number of fixing spins. The vertical axis is the minimum energy gap between the ground state and first excited state during quantum annealing. When error probability equals to 0, minimum energy gap expands as number of fixed spins increases, with degree of expansion depending on subproblem size. This expansion helps reduce the annealing time required to reach the ground state. When error is exist in fixing spins, we can also confirm the energy gap expansion by fixing spins. However, there are no clear dependence of error probability and minimum energy gap. The one reason why there are no clear dependence of error probability and minimum energy gap is this is a small size system. And so there are possibility to expand the large system. There are confirmed error probability dependence between error probability and minimum energy gap. These results, this energy gap properties explains the advantages of fixing spins obtained in previous study. To summarize our findings in this first study, first, experiments on DF annealer revealed a key trade-off between error rates, error probability, and number of fixed spins. This trade-off determines the optimal balance between error probability and annealing time, accuracy, annealing time. And next we conduct the energy gap analysis. We found that expanding the minimum energy gap during quantum annealing is important, and the fixing spins, it can expand the energy gap. However, many aspects of this phenomenon remains unexplored. For example, the dependence of the error probability. In the future, the fixing spins can be applied in parallel quantum annealing, allowing problems to be solved more efficiently on real quantum annealers. However, a crucial challenge remains. The one challenge is expanding the energy scale by expansion of the energy scale by fixing spins. While fixing spins can enhance the performance of quantum annealing, the energy scale is also impact the performance of quantum annealing. So, investigating the energy scaling, the relationship between energy scaling and fixing spin is important. That is future work at this time. Okay, and this is the first study. The next one is on archive. The title is Impact of Fixing Spins in the Quantum Annealer with Energy Scaling. This study is deeply related to the previous discussion. I will explain the purpose and the background of this study. While fixing spins is effective to deal with large combinatorial optimization problems, but sometimes generate large parameter values of Ising model. If the parameter values exceed the hardware's parameter range, we have to rescale the energy scale. But the effects of rescaling is not revealed in quantum. This study investigates trade-off between fixing spins, between the effects of fixing spins and energy rescaling. In this slide, I will explain the energy rescaling. The rescaling is a method to change energy scale, keeping the configuration of the ground state. When we reduce size of the Ising model by fixing spins, large longitudinal magnetic fields are generated. So the scaling is required to input the program into an actual hardware. This diagram shows the explanation of rescaling. The reduced Ising model generates large magnetic field. For example, the parameter range is -10 to 10. This is exceed the hardware parameter range. And so we have to rescale the energy to input into the hardware. By dividing each parameter by certain rescaling parameter uniformly, the ground state configuration remains, and we can obtain the reduced and rescaled Ising. In the current hardware, the rescaling parameter is determined so that the maximum absolute value of the parameter corresponds to the maximum parameter range of the hardware. Here is the settings and notations in this study. Hamiltonian of quantum annealing and the reduced Hamiltonian of reduced problem is the same as the Hamiltonian before I introduced. The Hamiltonian after rescaling is reduced problem Hamiltonian divided by the rescaling parameters. So the quantum annealing is performed following this Hamiltonian when considering rescaling. This is the definition of parameter range. In this study, we investigated the effects of fixing spins and rescaling through both simulations and experiment on actual hardware. To simplify the problem, we used fully connected ferromagnetic ISK model. We also defined error probability presented in the previous presentation. That is the same definition. The setting on the annealer is shown in this table. The embedding method is used minor embedding. At that time, the chain strength is fixed value 2.0, which is the maximum value we can set in the actual DF annealer. The number of leads is 100, and the auto-scale method is false. We use advantage systems 6.4. And we also investigated energy gap. The energy gap is obtained by exact diagonalization and analytical calculation at some dynamic limit. Okay, this is the results of on DA vanilla. Each panel shows the energy with different error probability of fixing spins. The horizontal axis is the number of spins of the reduced problem, and vertical axis is the rescaling parameters. Figure A shows no errors in fixing spins. Figure B shows error probability is 0.1, and figure C to F shows the results with more errors. Apparently, the low energy is obtained when error probability is small. And as the number of spins of the reduced problem decreases, the lower energy is obtained in all cases. And so fixing spin is advantageous in quantum annealer. In perspective of rescaling parameters, when rescaling parameter is small, the energy obtained by DF annealer is also decreases. And so the larger parameter range is required in hardware. As shown in panels D, E, and F, high energy points appear when the number of spins is large and the rescaling parameter is small. This result suggests the occurrence of chain breaking. The chain breaking decreases performance in this case. Now let's briefly explain the energy behavior of the presented in the previous study. First, we analyze the maximum values of local magnetic field after fixing spins. The maximum values of local magnetic field when fixing spin is given by this equation. This equation holds universally for all models. When it comes to considering a homogeneous Hattori connected ferromagnetic Ising models, we can denote the longitudinal magnetic field after fixing spins denoted by this equation. When we assume no errors, this value corresponds to the maximum value of longitudinal magnetic field after fixing spins. Considering error probability, we can denote the magnetic field like this. This behavior of the magnetic fields results in the behavior of energy obtained by a D-wave annealer. As number of spins of the reduced problem is small, or error probability is small, longitudinal magnetic fields increase like this, from this equation, leading to lower energy. The number of spins of reduced problem and error probability have a multiplicative relationship and deeply interconnected. As the scaling parameter is small, longitudinal magnetic fields increase, leading to lower energy. This is similar to this graph. The occurrence of chain breaking also explains the magnetic field. When number of spins of the reduced program is large and the scaling parameter is small, in this situation, because the chain strength is a fixed value for all models, the relative chain strength becomes weak. The relative chain strength, weak chain strength results in the chain breaking. This results also propose that fixing spins helps prevent chain breaking. Next, I will explain.
Tomohiro, you have another two minutes, so I recommend to wrap up your presentation.
Okay. Okay. The next, I will explain the energy gap properties. The horizontal axis shows number of spins, and the vertical axis shows the minimum energy gap during quantum annealing. When the scaling parameter is small, the energy gap increases as the number of spins of reduced problem increases. And so the results indicate the positive effects of fixing spins. On the other hand, when the rescaling parameter is small, the energy gap increases as the number of spins of reduced problem increases. And so when the scaling parameter is small, there are negative effects of fixing spins. In the middle range of rescaling parameters, there exists an optimal number of spins which maximize the energy gap. And so this result demonstrates the trade-off between the effects of fixing spins and the rescaling. This is the result. This is also results of energy gap with error in fixing spins. We can also confirm the trade-off relationship when fixing spin includes errors. When error probability is large, the dependence of the fixing spins and the scaling parameter becomes weak. Finally, we examine the effects of fixing spins at the thermodynamic limit. This equation is derived in the previous study. When not considering parameter range, the Since the number of fixed spin is negligible compared to total system size at thermodynamic limit, the effects of fixing spins are only affect adding local magnetic field. So the horizontal axis is magnetic fields after fixing spins. When not considering parameter range, the energy gap increases when the magnetic field is large. However, comparison between same parameter range, which is shown in black lines, there are trade-off between large non-magnetic field and rescaling parameters. So we can also confirm the trade-off relationship between fixing spins and rescaling in thermodynamic limit. So we think the behavior can be applied with different number of. This trade-off is similar to the analysis infinite size. So we think the behavior can apply with different number of spins. This is the conclusion. In the future, we have to investigate the other models, such as randomized model and combinatorial optimization preference with constraints, which is the more real, near to the more real application. That's all of my presentation. Thank you for this.
Tomohiro, thank you for your presentation. So it's time for question and comments. And I have some questions. So how you can guess the actual error probability of the device or algorithms? Are there any way to measure such error rate?
Actually, it is difficult to measure the error probability before using fixing spins. However, in my experience, the error probability is about 0.1. Is the there are frequently occurs. The case of 0.5 is randomly selected, and so this is the worst case. And this is the ideal case. The middle of error probability is in actual situation. So this result is the important in this study.
Oh, you mean that there's some way to determine the best parameter set when you conduct experiment with D-wave? Is
How
that
to
you? Mhm.
it is difficult to determine the best parameters before applying fixing spins in now. And so it is also the future work.
Okay, thank you. So we have another question. So
can I ask a question? Hello. Do you hear me?
Yes.
Thank you very much for the talk. I have just a question about, somehow related to the previous questions. At the beginning, you said that the fixing of spins is equivalent to consider an increased magnetic field. No, my question is, can you rather than from the beginning choosing a higher magnetic field without changing the structure of spins of the for instance Ising model that you are considering, and then it should be a priori everything the same. Have you tried to see the difference?
Okay, to choose the a method to choose values to fix and spins to which spins is fixed is studied in these previous studies, and these previous study already obtains high quality solution to large combinatorial optimization problems with using fixing spins. And so to select the to select the magnetic fields to select the spins which enlarge the magnetic field is the difficult, but in the previous study, they can meticulously find the values to fix and selecting spins like these properties, like following these properties, enhancing the values of magnetic field. And so choosing the best value is difficult in practical now, but the choosing better parameters is now conducted in this previous study.
Okay, thank you.
Thank you. So any other questions? Comments? Okay, if not, thank you again, Tomohiro. And I'd like to close this seminar. Thank you. Bye-bye. Have a good day.